Hello everybody, my name is Tomas Farid and I will be participating in the Challenge Program of 2014. Today, I am going to walk you through the steps of a problem in the Math 1008. Math 1000. So the problem says the volume of a sphere of radius r is given by the formula V equals 4/3 pi r cubed. So I'm going to go ahead and write that. 4/3 pi r cubed. That's the formula of this sphere we have right here. So, it's being filled by an incompressible gas. Let's say it's kind of a hole here, and it's being filled by an incompressible gas at a rate of 25 cubic inches per second. So, that means that the balloon is increasing, the sphere is increasing in volume. Its volume is getting bigger. So this 25 cubic inches per second is telling us that this is the rate at which the volume is growing. And so this right away tells us that we're dealing with a problem of related rates. So the way we approach this is we denote that 25 as dV dt. So we're going to say dV dt is equal to 25. Now, it's important to note that it's positive 25 because it's growing. If it were to shrink, it would be negative 25. So, then it says, how fast is the radius of the balloon changing? The radius being the distance from the center to one of the extremities. How fast is the radius of the balloon changing when r is 18 inches? So, r is equal to 18 inches. And now we're going to want to find how much the radius is changing. And now it's important to see that the rate at which the radius changes is not necessarily the rate at which the volume changes, because at the beginning the volume might be increasing at a constant rate, but the radius is increasing at a much quicker rate than the volume. So we have to understand that they're not the same, but they can be related. Now the way that we relate them is using this formula, V equals 4/3 pi r cubed. Now we don't use exactly this formula. What we use is a differentiated form of this formula. So what we do is we differentiate both sides of the equation. So we have V equals 4/3 pi r cubed. Now, we have two variables, r and v. So we're gonna differentiate with respect to the same variable. And that variable is time, because everything here is how fast is it changing and how fast is it growing. So everything is with respect to time. So that's important to notice. So we have dV dt here, and it's the change in volume over the change in time. And see, this is a independent variable, which in most cases would be your x. So our x here is t. So everything has to be in terms of t. So we have here dV dt. Sorry if you can't see, gotta make it a little darker. Okay. dV dt is equal to, now since every variable is going to be treated like with respect to t, we're going to differentiate this. We're going to do the chain rule in a way. Like if you have let's say you have y over x equals 3, and you wanted to differentiate that. When you differentiate y, you have to do the derivative of y, which is 1, and then you multiply by dy dx, because that's the derivative of y. Anyways, point is that we're going to take r and we're going to derive that. So r to the third comes down, and it turns this, neutralizes this 3. So we're going to have 4 pi r, and then we subtract 1 from the 3, so we have 4 pi r squared. And then we take the derivative of r, which as we've seen is going to be dr dt, because that's the rate of change of r with respect to time. And this is what we're really looking for. This is what the question is asking for. How fast is the radius of the balloon changing? So now really what all that it's left to do is to plug in all the values that we have. So dv dt is 25, so we write 25. Sorry, this marker is, let's see if I can. Okay, 25 is equal to 4 pi, and then we can substitute in 18 for r. 18 squared dr dt. So all that's left is to multiply these and divide by 25, and I'll just trust that we all have the ability to plug these numbers into the calculator. And the final answer, since pi is a transcendental number, we can say it's about dr dt is about 163. And so that's the answer. And this is, it's important always to place the units. This radius is in inches. This is inches cubed per second. So this is inches per second, because that's how fast it's growing. And now if you think about it, it's pretty big. Like it's growing, the radius is growing very quickly. Well, hope you enjoyed the lesson, and I will see you in a few days.